Good afternoon, everyone. Welcome to our Transportation Innovation Series. My name is Dr. Kevin Womack. I'm the Director of the Office of Research, Development, and Technology within the Office of the Secretary here at the U.S. DOT. It is my privilege today to introduce Dawn Marshall from Safer Sim at the University of Iowa. Ms. Marshall is a research manager with the National Advanced Driving Simulator and the Director of Safer Sim, a Tier 1 University Transportation Center located at the University of Iowa. As the Director of Safer Sim, she leads a multidisciplinary team of researchers in the areas of human factors, engineering, computer science, and psychology who use innovative simulation approaches ranging from microsimulation to human-in-the-loop simulation to promote safety. Safer Sim is able to study how road users, roadway infrastructure, and new vehicle technologies interact. Certainly a major issue these days with the oncoming of automated vehicles and V2I and V2V communications, and how we interface with each other using microsimulation and state-of-the-art driving, bicycling, and pedestrian simulators. Today's presentation will discuss the strengths of human-in-the-loop simulation in general and specific applications of simulation for drivers, bicyclists, and pedestrians to understand extremely important transportation safety issues. And of course, as we all know, safety is the #1 priority here at the U.S. DOT. So we're pleased to have Ms. Marshall with us today, and it's my pleasure to turn the time over to her. Ms. Marshall.
So thank you for coming. As said, I am Dawn Marshall, and I'm with Safer Sim. Safer Sim is led by the University of Iowa, and yet we are a consortium of 5 institutions. We also have the University of Central Florida, where we work with Dr. Mohammed Abdelhadi, and the University of Massachusetts at Amherst, where we work with Dr. Mike Nodler, and the University of Puerto Rico at Mayagüez, led by Didier Valdez, and the University of Wisconsin, where we work with Dr. David Noyce. And at each of those locations, we have additional PIs and researchers. Those are just our directors. I am also work with Drs. Joe Carney and Jody Plummer at the University of Iowa, who are associate directors there. Can you all hear me? Okay? Okay. Our center themes, particularly with our new grant, focus on automated vehicles, connected vehicles, vulnerable road users, roadway infrastructure, and then distributed simulation technology. And I am going to touch on each of these in multiple ways throughout my presentation. One of the things that simulation does well is it brings together people to collaborate, particularly people from many different disciplines and backgrounds. The simulator doesn't care what the background of the user is. So we can use simulation no matter what our background. It's often typically thought of as an engineering tool, but at Safer Sim, we have, of course, people in civil engineering who are looking at infrastructure, but we also have people in public health looking at how vehicles interact and designing interventions so that they can improve public safety. We have individuals in computer science looking at the technology of simulation and how to improve it, and also what questions can it actually answer. We have people in education who are trying to understand how educating people about their vehicles and driving safety or transportation safety, and how different education methods work, and they're using a simulator for that work. Of course, we have industrial engineering, and that's my background, where people are looking at primarily the ways that drivers interact with their vehicles, but also how pedestrians interact with vehicles and how bicyclists interact. So the whole field of human factors is under industrial engineering. And in kinesiology, they're looking at how people actually sit and move and behave in their vehicles. And psychology, what do people perceive and understand around driving and transportation safety. Pharmacy is a particularly interesting partner because they are looking at both prescribed medications and over-the-counter medications, and not only the impairment that may be caused by them, but how do we measure impairment that we're unaware of. Driving is a complex task that uses both our cognitive abilities, all of our senses, and our physical abilities. And so that question goes both ways. How impaired is someone 2 days after anesthesia? And then also, does this drug or this particular medication impair people, and for how long? So that's a particularly interesting question. Emergency medicine is not someone that most people would think would be involved before the fact. In fact, they see the crash victims after the fact. But by telling them what happened during the crash, they know they can know more about what injuries to expect. And then because they see the injuries, they can tell us more about what we might need to look at during crashes or immediately before a crash to understand how to prevent them. So that is also a two-way street. And again, we're a very collaborative center. That's actually something we're very proud of. We often have engineers working with each of these other disciplines, or we have computer science and psychology working together across departments and then also across institutions. It's a very, very much a strength of our University Transportation Center. So I'd like to start out with discussing simulation itself. Simulation, of course, has some strengths. It's a very useful tool. For one thing, it's repeatable. We can provide the same conditions, the same study conditions, the same test situations to multiple people repeatedly. And we can do it across different geographic locations using multiple simulators. It's also controlled in that we know what those conditions that we are presenting are. We choose the time of day, the weather, the road conditions, all of those things. We can also, because it's controlled, vary those conditions and look at, say, the difference between a situation at night and the situation during the day. And we don't have to wait for those conditions to naturally occur. And we know that the conditions were the same every time. It's cost effective, even though it doesn't always seem that way. We can develop a study in a matter of months, say, compared to implementing real-world applications or interventions, and collect that data in, say, 6 months, rather than building something over months and then collecting data for a year. We can also change very quickly. So if we want to look at several different treatments in an infrastructure situation, we can look at all of them at the same time and narrow them down and then move on to other data collection strategies to choose the correct one. So, and the other thing that gives us is a very focused data analysis. Because it's repeatable and we have so much control, we can truly focus on some very specific questions and have some very powerful data, whereas other methods, while they have their strengths, they may not have the statistical power we can generate with simulation. We can also specify where people drive, walk, or bike. So we choose the location. We can choose it for its attributes. We can change those attributes if we want to, but it's, again, a part of that control. So we're not waiting for people to encounter the situation that we would like to look at. But the biggest strength of simulation is that it's safe. We can look at potentially very dangerous situations and not cause injuries. We can look at crash situations where someone would have to respond perfectly, whether they're a pedestrian, a bicyclist, or a driver, where they'd have to respond perfectly to avoid the crash, and yet if they don't, they're not injured. And we have all the data we need to understand what happened in the few seconds leading up to that. Now, We can also, I should touch on, we can also look at impairments. I've already discussed medications or other drug-related impairments in a safe manner. We'd never want to get someone drunk and put them on the road, or dose them with marijuana, cannabis, and put them on the road. So we can look at those things in a safe environment. We can understand the impairments themselves. We can also look at things like distraction, which, if you ask most of us out where we are, is just another impairment. But we can look at different types of distraction, again, in a very safe manner. And we can also look at different road conditions. We can put people on an icy road where they may need a traction control system, or a heavy truck may need a rollover prevention system, and we can look at that in a safe way without actually them experiencing that crash. Now, what simulation is not. Simulation is not a pedestrian or a driver driving their vehicle or walking in their neighborhood. It's something different. We have to take measures to make sure they're familiar with the things, the car they're going to drive or the route they're going to take. So that it's not that. It is not behavior collected over time. So we don't have, say, 6 months or a year of driving data for a specific individual. We have performance data for a few minutes in a specific situation. One unfortunate aspect of simulation is it may cause motion sickness. It's not nearly as common as it was 10 years ago or 20 years ago, because simulation technology has gotten better, but it is still a risk. 20 years ago, about 20% of people who went into driving simulators experienced some motion sickness symptoms. Today, in our big advanced simulator, which I'll talk about in a little bit, we get about 2 to 5% of people experiencing some symptoms. So that's a big difference, but it's still there. And there's no real way to predict it. If you get motion sickness in other situations, you may be correlated, but we don't know for sure. And so it's a risk. And it's not appropriate for some maneuvers. Simulators aren't good at things like parking or backing up because of the changing points of view. You have to look over your shoulder, and we're projecting scenes, and they need to be from a specific eye point, and they're adjusted for the use of your mirrors while you're driving down the highway. And so changing that point of view is more difficult in a simulator. So there are some things simulation doesn't do well. So now I'm going to talk about the different kinds of simulators. I have worked at the National Advanced Driving Simulator with driving simulators. And as I mentioned, we look at driver performance. Some of the topics are automated vehicles, connected vehicles, roadway features, and historically we've done a lot of looking at safety features within vehicles. Recently, we've been looking at transfer control questions, timing, reliability questions within that. What the simulators do well is they collect a great deal of data over a short period of time. So in the center, sort of to the left, is the NADS-1 simulator, and that's the most advanced driving simulator in the US. It has 13 degrees of freedom, so it moves inside a bay on X and Y rails. You can see the hydraulic legs. There are 6 of them, which give us roll, pitch, and yaw. We have a turntable, which gives us rotation. And then inside the dome, there's a full vehicle cab with actuators where the wheels would be. So we get road texture, seams in the roadway, gravel, those kinds of things. That simulator is very useful when you need motion cues, such as out of control, spinning, fishtailing, rollover in trucks. The motion cues there are very important, and we need the motion system to give the drivers basically their ears, those motion cues. At the top you see NADS-2, which uses the same cabs, but it's a fixed space simulator. It has no motion, and it has a smaller field of view. And then in the lower right you see a mini sim. And these, once again, doesn't have any motion, uses a real vehicle seat and a steering wheel. These are illustrating different levels of fidelity. So as you get away from real driving, you've got lower and lower levels of fidelity. And of course, we all want to say our simulator's high fidelity. Even us, we would love to say all three of these are high. I would call these high, medium, and low. The medium because you're actually enclosed by a cab, and you're dealing with real instruments in a cab. The mini sim on the bottom, while you've got a real seat, real pedals, real steering wheels with the actual loaders that would give you the feeling of driving those, you're not enclosed by a cab, you're not wearing a seat belt, things don't sound exactly like they would in a car because you're not enclosed. And yet, each of these simulators is able to answer specific questions. If you don't need motion cues, you don't need the motion. If you're only looking at speed and lane deviation, you can use a lower fidelity simulator, which is faster and less expensive, to answer the questions. It's all about finding the right tool for the questions you're asking. Oops. Pedestrian and bicycling simulators. We also have the Hank Lab at the University of Iowa, and I really should speak about these differently, but I put them separately, but I put them together because they both use the same environment and they switch back and forth. They are virtual reality caves that, with a bicycling simulator, they put the bicycle in, and the bicycle's base is fixed, and yet the pedestrians actually pedal, and the scene moves past them. They can stop, they choose their speed, but they have to go straight. They can't turn. In the pedestrian simulator, which uses the same cave, the participants wear a helmet that tells the simulation where they're standing, where their head is turning, when they begin to move, and when they stop. And that the cave is deep enough that they can cross a single lane of traffic and then come back again within that cave. And some of the things the simulators have looked at is interaction with vehicles, different infrastructure strategies for, say, the bicycle. We are about to look at some implications for automated vehicles. How do those vehicles in that simulation behave, and how do the pedestrians make choices around it? Some of the past research they've done is peer influences. So if you're standing on a sidewalk at a crosswalk, how likely are you to start crossing the street if someone next to you starts, maybe before the signal changes? How is that different if you know that person or if you don't know that person? Also, street crossing, particularly with children, what gaps do they choose? And again, also what their peers influence. And then we talked about the gap choices. The interesting thing they found about children is they choose the same gaps as adults in general. I'm oversimplifying this greatly, but they tend to choose the same gaps, but they have trouble getting started as quickly. They don't prepare, and so they don't start until the gap is there, so they end up with effectively much shorter gaps, and that's really interesting information about younger people. And then it would be interesting to go to, say, older people and see how their gap choices affect their safety as they're crossing streets. Another topic we're working on is advancing simulation itself. Any tool that is static is going to become out of date relatively quickly. The most exciting thing I see that we're all working on, it's not even upcoming or on the horizon, lots of people are working on this, is distributed or connected simulation. We're also we can bring real-world roads into a simulator. In the past, that's been an intensely manual process where people had to go out and take very detailed measurements and then by hand build those environments for the simulated environment. It was labor-intensive and took a lot of time. It was accurate, but it took away from the benefits of simulation where we can get things done quickly. I've mentioned that there are lots of platforms of different simulators. There are different makers of simulators, and they all use their own software architecture. And so something developed on one simulator platform could not be transported to another simulator platform easily and recreated there. So if we wanted to do something, the same study at several locations around the U.S., we had to ensure we were using the same simulator platform. And then also the realism of avatars or other people in the simulation. That's also going to become key as we're looking at interactions. These are all things that we are working on here at SaferSim. Those are all topics that we've done some work and we have plans in the future. There we go. So distributed simulation or connected simulators, as I said, I think this is the most exciting advancement in simulation that's coming along. Many people are working on this. They've connected multiple driving simulators. The pedestrian and bicycle simulator at the University of Iowa, they now have 2 caves, so they can connect. They'll be able to look at 2 pedestrians at the same time, or 2 bicyclists, or a bicyclist and a pedestrian. But we also have plans to connect driving simulators to those pedestrian and bicyclist simulators. So in theory, in the next couple years, we'll be able to look at a bicyclist, a pedestrian, and at least 1 driver, possibly 2, all at the same intersection, and looking at the choices they make there. What's really interesting about distributed simulation or connected simulators is that conflicts happen all the time between road users. Every several seconds, there's a conflict. But we all work very hard at resolving those conflicts before they become dangerous, which is why crashes are relatively rare events. But when a crash happens, the injury or potential death is a significant factor. So if we can start understanding those interactions and how those conflicts are resolved, then we can understand how when those conflicts move past the point where they can be resolved, what happened or didn't happen that the crash actually occurred. And that's very exciting because humans don't want to get hurt. We're very good at giving each other space, but what was it that we didn't give the other users the space to get through to resolve that conflict? And distributed simulators will allow us to do that. This relates very closely to the avatars that I was talking about. In the past, pedestrians didn't need to look particularly real. They may actually be just flat images of things. Other drivers in cars didn't need to necessarily turn their heads or move their arms on the steering wheel because mostly it was just a vehicle that was out there. It's all about what level of realism do you need to understand the situation. Well, if we're going to understand how people interact at that intersection that I described, and do they look at each other, do they wait, what kinds of things do they do, then we need to be able to make those avatars realistic. And what level of realism is needed for those avatars? Is it enough that it is an avatar that turns its head towards the pedestrian so that they know the driver's seen them? Or does it need to blink? And we don't know the question to that yet. We don't know the answer to that question yet, but that's part of what we'd like to look at. And it seems like you'd want it to be as realistic as possible because that's the coolest thing to do, but it's also the most expensive thing to do. And so the question really comes, what do you need to make these interactions realistic so that people believe them, immerse themselves in them, and behave the way they normally would? So we're working on that. Automated vehicles is also a very interesting topic, a very hot topic. But the power of simulation is we can look at systems that do not yet exist. You can't do an on-road study with a vehicle that hasn't been built. So in a simulator, we can look at different levels of automation, different kinds of automation, different behaviors of automation that don't exist. And we can start to understand how to design that automation so that it's safer, so that it takes some of the guesswork out. We've already done some work on transfer of control. Many people have, and what it will take for that. We've done reliability and trust. Some of the most interesting work I think we're doing is on driver state detection. So how does that vehicle know what the driver is doing during its automation mode, and can the automation change the way it interacts with the driver based on the driver's state? Some examples would be, is the driver reading or are they asleep? It's going to take a reading person a lot less time to become situationally aware than someone who's sound asleep in their vehicle. Also, can the vehicle sense alcohol? Can it sense any other kind of impairment? And should the automation change the way it behaves if someone in those states are in the vehicle? We're not suggesting that we make those states safer, but just what are the safety concerns and benefits associated with automation for people in different states who are actually sitting in that vehicle? Another question is, how do you distinguish the passenger from the driver? You know, is it that you've got 4 people who have been drinking, and so there's a lot of alcohol being exhaled into the air, but you have a designated driver, and in which case that person's safe to drive, but no one else is? So there's a lot of very complex questions here about how we deal with impairment. What about people driving themselves home from surgery? Is that possible? We're all advised not to, but if you have some automation, could you from outpatient surgery? That goes into the pharmacy work we do with the Department of Pharmacy. What level of impairment? When is the impairment sufficiently abated? How long does it take? Does it take 2 hours when the person's awake and can talk to you, or does it take 2 weeks before their response time is really back to normal? Those are all really interesting questions. And then what level of automation might be appropriate in that situation or inappropriate, even if it seems like a good idea, because they wouldn't be able to regain control. So driver state detection is a very exciting area. Connected road users. We, at least in the work I do, we talk a lot about connected vehicles. What we don't talk a lot about is connected pedestrians or connected bicyclists, and yet that's some of the work we're doing. Can vehicles send signals out that, say, a smartphone application can pick up? Not assuming that everyone would have a smartphone, but if a large percentage of the population do, it would be silly not to take advantage of that fact and give them the opportunity. But then you don't want the vehicles assuming that everyone has it. So signals, can we connect pedestrians with the infrastructure or bicyclists with the infrastructure so that when you get a vehicle to infrastructure connection, that the infrastructure can inform the vehicles about all of the bicycles, maybe there's 2 or 3, or all of the pedestrians there, or if it can assume things. They're very open questions, but can we connect everyone into the system and find ways of making things safer without making the assumption that everyone's connected? Just like not everyone's going to have a connected vehicle right away or an automated vehicle. I turn my cell phone off. I'm probably not going to be one of the people who's going to be able to benefit from this right away. And yet, if we found a benefit, I might turn it on and put it in my pocket and let it vibrate if there is a benefit to it. So, pretty good. I've talked a lot about vulnerable road users as I've come along, but I want to talk about them specifically. We've talked about pedestrians and bicyclists, but there's also road construction workers, people who have to be in the roadway for their job, and how can we look at situations and different, say, work zones, setups that may be safer for them without having to actually test them in work zones? Can we look at different age groups, such as the children I was talking about who choose the same gaps as adults but don't start as early as adults, or the elderly? Can we look at those different populations? Again, using simulation so that we can understand what's different in a safe environment. Because after the fact, people don't remember what really happened. They remember what they thought happened, or they were thinking happening. And in simulation, we can look at what was really happening. When did someone start moving? When did someone release the accelerator? When did they start braking? Exactly how much were they steering? We can look at that with bicyclists. We can use eye tracking software to see where they were looking at a specific moment. And so what we can understand is how that unfolded. What I was talking about earlier, those conflicts and how they resolve themselves or not, that's where the power of simulation is, and particularly connected simulation, because we can gather that information for all of the users in that situation, and then really begin to take it apart and see how people are interacting. And I think this will be particularly powerful for the vulnerable road users, because they're the ones who can't tell you what they were hit by a car. They cannot tell you what that car was doing. But in a simulator, we can tell you what the car was doing. We either programmed it or we have data on the other driver, so we can start to understand those situations without actually putting people in danger. And I think I've touched on all these topics, but it's very interesting because vulnerable road users are interesting across all the different types of simulation, and they can be incorporated everywhere. I've alluded to this, roadway infrastructure, where we can set up different work zones, we can apply different treatments and understand how they may or may not be effective. One of the things that I find really interesting is that not only can we take those dangerous situations, those sections of roadway or intersections that we see crashes, higher crash rates, but we don't know exactly why, because you only get the information that there was a crash. You don't know what was going on in the 5 seconds before that crash. So that's what simulation can tell us. We can create that real-world location in a simulator and then collect that data and even maybe control those conditions a little bit. We ask people to do different things to see if we start seeing the pattern. These are some of the studies that we will be in the next year starting up on infrastructure. The other thing about infrastructure work is that we can actually build it in a simulated environment before it's built in the real world. So we can start to identify either issues that it may happen or how people will respond to it. Or the more likely case is we can start educating them about how it will work. Particularly communities that are resistant to new intersection designs or new technologies, we can demonstrate it to them and explain it to them so that they become accustomed to it before they actually have to drive it, walk it, or bike it, so that they know how to use it. Because a lot of times when something new comes along, there are more conflicts, and sometimes more crashes, immediately after a new implementation because people don't understand. And those conflicts actually happen when someone in this group of road users does something the other road users don't expect. So if they've all seen it and we've been able to teach them about it, there's less likely that people are going to do something the others don't expect. And this, finally, simulation is a really interesting way, a wonderful way to get people interested in both technology, but also transportation in general. Not just the safety, but transportation as careers. We've helped develop a global road safety course. We have a physics curriculum that has a simulator that goes out to schools. We also have teachers who bring their classes into our simulation facility, and we talk about all the different backgrounds of the people who work in our center. You don't have to have an engineering degree to work in a STEM field. It helps, but it's not necessary. We have people with English degrees. We need them to help us write our reports, right, so that you all can read them, and we've used good grammar. We need people in computer science, but we also need people with an art background so that our scenes look interesting and realistic. those avatars are going to, we need the computer science to animate them, but then they also need to look like people and not robots, that kind of thing. And I find that students who come in are very excited to find out that we're not all computer programmers or all engineers, even though there's several of us, but there's a way to be interested in STEM even if you don't feel like you want to major in physics or engineering. And so those are the tours. And finally, the portable simulator. We have two kinds of portable simulators. You can see one of them in the upper picture. It's a very low fidelity simulator. It runs on a laptop and a TV monitor. What that gets us is we can load it into two cases and it fits in a sedan. And we can take it to schools. We take it into physics classrooms where they collect driving data on different road surface frictions. And then they have to analyze their own data. We provide them that data. We give them examples, and they try to match the set, but then we give them their data, and the next exercise is a data analysis tool using Excel. And the kids are very excited about this. And I don't know about you, but I wasn't that excited about Excel when I first learned it. But they get excited about it because they understand that there are real-world things, very interesting things they can do with these tools that they are learning. I listed teachers because we teach teachers how to use our simulator, but a number of our teachers have actually asked if we have internships for teachers. We have internships for high school students and college students, but the teachers want to come in and learn about simulation as a tool. And the more excited teachers are about the technology that's out there, the more excited the students are going to be. So that's a very exciting thing. And at the bottom is a statistic that I'm very excited about. In 3 years, we allowed 37,000 people to have experiences, transportation safety experiences. There are two ways we did this. We did this with the portable simulator that goes around to schools. And then the other one that I haven't mentioned yet, it's part of a mobile museum that's a converted RV. And there's a simulator, a driving simulator, as one of the exhibits in that RV. And it goes out to schools and fairs and other events. And so we were able to get simulation out there in the public and give them experiences with it. And then they come back and they remember that it's something they can do. So that is the end of my slides. Thank you very much for your kind attention. I think we'll take questions if we have any. Yes.
I have a question about validation.
Mm-hmm.
And it's, a question about validation. I'm not so concerned about the validation of, say, the underlying physics models or anything like that, but what I'm questioning is the validation of essentially the outcomes and the interpretations. For instance, does a human behave in these scenarios similarly to how they would in real life? And as you know, comparing simulation results to, say, naturalistic studies, there's been some conflicting information. So I'd like to know what type of work you're doing in research and development to maybe close that gap or understand that better.
That's a great question. I'm glad you asked it. So yes, there are differences in, say, predicted crash rates between simulation studies and naturalistic studies. And that goes back to that conflict resolution that I was talking about. Often in a simulation study, we're looking at the worst case scenario. We're putting people in a situation where it's very difficult to avoid that crash, because that's what we need to know, is how, at the very last second, can that crash be avoided. Naturalistic studies are looking at data, collecting data, where people are free to try to resolve those conflicts. What we do to try to bridge that gap, in the past, what we've done is we've collected on-road studies and simulator data where we've matched the route and the geometry of the route, and we've looked using an instrumented vehicle, and then the simulator, we've looked at driving behavior in the two situations. So we're validating the simulator that we get realistic driving behavior in the simulator. It depends on the age group and the condition, but we've gotten between a 5 and 7% difference, which isn't a lot, say in lane position or driving speed. So we're fairly confident that people drive, when we ask them to drive as they normally would, and we allow them to become familiar with the simulator, we're fairly confident that they are driving as they normally would. The one caveat there is in a simulator, they know they're being watched. They know they're in a study. Whereas when we're driving home, that, we're 15, 20 minutes into our drive. It's a drive we make every day. We're pretty sure nobody's watching us, right? So there may be some behavior patterns that are different. Because we can't measure the actual 5 seconds before a crash in the way we do in a simulator, I can't tell you what I can do to validate that, except to understand that people were driving in essentially the same lane position and at the same speed that they were at the beginning at time 0, and then at 5 seconds later that crash has happened. That's what I can tell you. But the performance during that 5 seconds is the power of the simulation. The other thing I'd like to respond to is that's part of the reason distributed simulation or connected simulators are going to be so powerful, because it's that interaction between people that that transforms the cannot avoid a crash situation that we put people in a simulator to understand that conflict to where people have managed to avoid that conflict. And it's those interactions that allow those situations to unfold safely rather than with a catastrophic end. And so that's why connected simulation or distributed simulation is such an exciting thing. And that's going to take a lot of validation. There's work to be done there, but it's very exciting. Did I answer your question? Okay. Yes, sir.
I'd like to know as to how much of the virtual reality technology that your specific center has leveraged, and in what sort of applications?
Okay, so at the National Advanced Driving Simulator, which is the one I know the most about, we have a unique software architecture. While we may purchase software packages such as image generation software, which we used to do, we have now written our own. So we don't, say the gaming industry, we don't utilize, at our center, we don't utilize that very much, because we need very deep and specific control over the software. And when you purchase a product, they don't really want to let you into their code. That being said, the Hank Lab, where the pedestrian and bicycling simulators are, use open source code. They buy software, and their simulators are built on these things. So simulation uses, across different centers, uses a very wide range of different software, and whether it's something that you can go buy or if it's something that was written in-house really depends on basically the needs of that center. Or that's my understanding. Did I answer your question? Okay. Yes.
Hi, thanks for the presentation. My question is, are you doing anything with organizations or institutes outside of the U.S.?
As a center, a research center, yes, we are. We have relationships with automobile manufacturers, OEMs, outside of the U.S. We are trying to collaborate with other research centers. Finding a way to do those is sometimes difficult because the funding issues. It's something we don't do as much as we'd like to. As you may know, that other countries or groups of countries have different views on the importance of safety and improve simulation safety much more than we do here. Here it's more of a as-needed kind of situation that we pay for the developments as we find we need them. Other countries will pay for the development of new technology because because they think it's a good idea. Sometimes it is, sometimes it isn't. So the basic answer is, we do, not as much as we'd like.
Thanks.
Yes.
What I'm wondering is how much data are generated from these simulations, and what kind of challenges do you have as far as storing and analyzing the data?
That's a good question. So the simulators out at the National Advanced Driving Simulator collect most variables at 60 hertz. So on a 20-minute drive, we have huge data files. What we do after that is we look at specific periods of time and flag those. So we're not looking at 20 minutes of driving. You've heard me talk about that 5 seconds before event, or maybe we're looking at 1 minute for lane departures. The size of the epoch, the length of time of the epoch depends on the type of thing we're trying to look at. But we tend to look at the data for the point in time where we believe things begin changing, or we look until they begin changing, and then we specifically analyze a smaller epoch. So we don't have as many data analysis and reduction problems as, say, naturalistic driving, where you don't know where the events are and you have to look at this very huge file. And that's why when I say we've got a very focused data analysis, we can focus our analysis where we know there's something we want to look at. And because we have control over the simulation, we can flag that data in an automatic manner a little bit easier. We don't have to review a video to find when someone was looking away. We can look at our eye tracking data and look at the data. So it's easier for us to find those interesting events. That being said, we collect a default collection is over 100 variables at that 60 hertz. So, and we collect video at 30 hertz. So we have a great deal of data. We just try to only use our resources looking at the specific portions of that data that are going to be interesting to answer the question we're trying to address.
Other questions?
Okay.
I heard you spoke about impairments.
Mm-hmm.
Do you include in not necessarily impairments, but people with disabilities, maybe somebody missing a limb, both inside and outside the car?
We have. So I'm not sure I mentioned it, but kinesiology was, we worked with the kinesiology department to look at some of the way people are moving inside their vehicles. We also have a study where we're looking at people with distal radius fractures, so their arm is immobile and they're advised not to drive for a while because they shouldn't put pressure. Those are very interesting studies because driving, it's not just about how to make drivers safer, it's when are drivers safe to drive. So drivers that are going to drive. So we do want to look at that. I think it's relatively new. I don't think people have been using simulation to look at those questions to the extent that we could have over the last 2 decades. My first study as an undergraduate research assistant looked at Benadryl and another antihistamine, and it was that study that was looking at impairment that got me hooked on this. So, but what I don't see as much of that as I'd like. But when we look at avatars, we're going to have to look at some of that stuff. We're going to have to look about how a broad range of people move and exist in the world and in their simulators. And so,
That was going to be my next question.
Right.
Can you create avatars that are...
yes. So the idea, it's new technology, at least to us, where we will be looking at actual movement inside vehicle spaces or at curbs and actual walking using different kinds of sensing devices so that we can collect that big data set and then start small and work out to find out where we find the realism point that we need. The other way to go is to start big and work down and then find that range that you really need. And that's part of our work that's starting right now, and we expect to have a lot more information about that within the next 2, maybe 3 years. It's not a short process.
Yeah. I know the scenario you gave. I really love the scenario when the smartphones and you cut yours off.
Mhm.
Factor in the fact that you have children who may not have.
Yes, right, right. And so there's a lot of technology out there that's not simulation technology, like pedestrian sensing technology that's actually, it's vision technology that's looking to see the pedestrians, and it works. And so there are some things where you don't need simulation to look for it, but there are other places where simulation can tell us about the possibilities, and then also what we may be, sounds like a good idea, but really isn't. Okay, I'm sorry.
Any other questions? Okay, if not, thank you very much, Don. We appreciate
Thank
it.
you.
Okay, thank you, everyone. We do not have a speaker scheduled for April in the Transportation Innovation Series, so I would suggest to you all that you keep an eye on the UTC website for future information on when the next session will be held in the series. So thank you all again very much for your attendance, and we appreciate Ms. Marshall. Thank you.